Hello everyone. Today I'm going to be talking about quantifying the maximum possible improvement in 2-parquet experiments. This is work that was jointly done with my PhD student Anusha as well as my former advisor Dan Fry. So I wanted to talk about this particularly because this is something that we worked on and we've published, and I think we made a contribution to the design of experiments. That's the broad area that it's called. But I also feel like somewhere the core problem is not solved. So part of this talk is perhaps to encourage some of you to look at this problem with fresh eyes and see if there's something exciting to do here. So I just want to briefly introduce experimentation, design of experiments, the broad space, because many of you might not be familiar with it. But I wanted to do it with something that you're all very familiar with, which is supervised learning. Like everybody here obviously knows what supervised learning is. So how is experimentation similar or different, right? They're both trying to solve the same core problem. It's a learning problem essentially. So when you experiment with something, what are you doing? You're poking it, playing with it, and then looking at how it behaves, right? You're learning something about a system, which is again similar to the learning problem of supervised learning. So in supervised learning, you have an X matrix typically and a standard regression problem, right? An X matrix, a Y vector, and we need to learn some function, right? Some F hat that you'll wind up learning that gives you the relationship between the inputs and the outputs, the features and the labels. In experimentation, we have the same problem. So we're also trying to do the same thing. But we have a unique challenge as well as an opportunity, is that we get to decide what X matrix is. So when you do an experiment, you're not deciding what the outcome is, but you're actually deciding what conditions you want to, how you want to operate the input variables. So it's not a passive consumption of observational data, which is what you might be doing in a supervised learning paradigm, but you actually have the unique opportunity to fix X and then go fetch Y, right? Now, this is a challenge because in addition to the problem of learning F hat, are some X matrices better than other X matrices, right? We all know the holy problem of multicollinearity that you have to deal with, right? And here you have the opportunity of not creating multicollinearity, right? Our columns don't have to be correlated. So what is the best matrix that you can kind of construct, which will help you learn the F hat in the best possible way? And so that's the opportunity we have as well as the challenge. The additional challenge of designing the matrix, but typically the learning problem becomes then fairly trivial, right? First of all, the scale is not big, especially if you take each variable. Here I've given you a sample of one of a 2-parquet matrix. So A, B, and C are just 3 of the input features, right? And each of them are explored only at 2 states, -1 and +1. So it allows for a linearity in the X matrix, right? So everything that you learn is approximated to a linear model of sorts. Even if you look at it as, even if I had 10, 20 features, the entire number of rows is 2 power 20. It's an easy problem to kind of, it's not a big scale problem, and you're not dealing with nonlinearity. So 2-parquet is exactly this. So when you say a 2-parquet experimental design, it just means you take each of your factors, k is the number of factors, here k is 3, and you do a complete enumeration of all the possible combinations. And so for each row, you go fetch a Y label. Now, obviously, you can see there are some basic properties to this matrix. This is called an orthogonal array. It just means that the dot product of any 2 columns is 0. You can also think of it as a correlation between any of them is 0. You can think of it in terms of balance, which is that every possible combination is explored exactly once, right? But I can go fetch multiple outputs for each combination, right? So this is essentially what a 2-parquet matrix is. So here, like in your supervised learning problem, you're trying to learn an F hat. Usually the purpose of learning an F hat is not just to stop with the function that you learn, but it is to maximize or improve a system. So obviously if you learn an F hat, it's easy to go figure out what the input should be set to get your best Y value, right? So the usual goal in experimental design is to maximize some Y by learning an F hat, or even without learning an F hat in some cases. And the learning problem is fairly trivial. So hopefully now I've introduced what design of experiments tries to do, which is come up with these cool matrices and then analyze data following that. So now I'm going to introduce a problem that we wanted to solve, right? So the problem we wanted to solve, let me motivate it first of all, which is that usually experimentation is expensive, right? Unlike passive observational data, which you might just fetch by observing, here you have to do something, right? It means you have to build something. It means you have to disrupt lives if you have to go experiment on someone. Some cases it means going and taking a really expensive car and crashing it to crash test, right? So it costs a lot of money to gather this kind of data. So if you want to do experiments, we need to have some notion of what is the possible benefit you can get from it. What is the maximum improvement that can happen? And so how could you improve something by experimenting? It's really simple. You learn an f hat. If you learn an f hat, you know how to set all your features. What are the optimal values that you set your features to maximize your y? So the improvement in y is what you're trying to quantify. What is the expected value of the improvement in y from the knowledge gained about f hat, which comes about from experimentation, right? So we're going to try and quantify that. And the goal of what we're going to try and do is say, even before I conduct an experiment, is there some way for me to get to the distribution of the highest possible outcome? So I've not done an experiment. I've not gathered the x matrix or y vector. But if I make some distributional assumptions about the factor fx, can I then translate that to the expected value in the improvement in y? That is the goal of what we're trying to do. Okay? The literature for this comes from multiple quarters. Obviously, the design engineering community has looked at this about how do you explore a design space sensibly. As you move more towards from design engineering, there's also the whole field in decision theory, which has looked at the concept of expected value of perfect information, expected value of sample information, right? The concepts are, again, in decision theory fairly straightforward. With more knowledge, you are able to adjust your input variables in a better way, and therefore you expect to see a benefit in the expected value of y than by setting the design or decision variables randomly, right? So the delta and y is what we're looking at, okay? And doing this using a Bayesian framework, which is having distributional priors for the factor fx, is something that my group and others have been working on for a while. Okay? So let me now formally just state the problem statement. I'm not interested in this optimization problem, but I'm interested in knowing what is the distribution if I were to optimize this function. So I want to optimize this function. This is just a simple general linear model. We stuck to a general linear model, again, because all the factor fx are linear. You saw the -1 + 1. But what you have is these interaction terms. So suppose I have n factors here. So I have n factors. I'm trying to maximize this function. And each of my x's, which are, how many x's do I have? I have n x's, right? Because there are n factors. So imagine I had 5 factors, let's just say that. So I have 5 betas and 5 x's, and each of these x's can be set only to -1 or +1, right? And then how many two-way interactions will I have? NC2, right? And then I'll have NC3, three-way interactions, right? An interaction term is nothing but just the simple scalar multiplication of xi and j. It's actually the reason why we decided to codify the variables -1 and +1. If you think about it, rather than calling it 0, 1 or something else, when you precisely have it as -1 and +1, you get the exact effect of what we call as an interaction. That is, what is an interaction? It's not the same thing as multicollinearity, because we've gotten rid of multicollinearity. The x's are not correlated with each other. An interaction just says that the effect that x1 has on y depends on what x2 is set as, right? And that's exactly what is being captured by the simple scalar product out here. So what we're trying to do is we're trying to maximize w. Again, this optimization problem is itself very trivial, right? Why is the optimization problem trivial? If I gave you this as an optimization problem, and I know these are the distribution of betas, but for a given function, you know the betas. Some will be negative, some will be positive. They're Gaussian in nature. If I give you a set of betas, what would you do to try and maximize W? Sorry? No, you get to set x's as, what if beta is negative? I might not want to set x's positive, right? Like I might want to set it as negative. So it's a trivial optimization problem because you can just do an enumeration. You can have this structure, sure, you've got n terms out here, NC2 terms out here, NC3 terms out here. But worst case, if you've got n is equal to 10, you have 1024 combination, just brute force it. You'll just see which is the best outcome for a given set of betas, right? So we're not as much interested in saying how do we solve the problem. That is fairly trivial. The point is, before I even go and learn what the betas are, and I will only learn the betas by experimenting. I don't know what the betas are, but I do have distributional priors for the betas. Can I upfront can you tell me what the distribution of W will be? If I give you the distribution of betas, knowing that you will set the x's such that you will want to maximize W, what is the distribution of max of W? That's the problem we are trying to solve. At the very least, can you tell me what is the expected value of the max of W? Assuming you use a foolproof algorithm, and to think of a foolproof algorithm is not hard, right? There is a perfect correct answer. The enumeration will tell you what the correct answer is. Okay? So this is what we're trying to solve. And this problem, let's start with really simple cases where n is equal to 1 and 2. You'll see how easy it is. When n is equal to 1, right, this is y is equal to, forget about the beta naught, beta 1 x1 plus e, where x1 is minus 1 or plus 1. Now, what is the distribution of y of x1 if beta 1 is normal, 0, sigma m? Again, y of x1, what I meant is max of y of x1 out there. I'm clearly going to try and do this optimization where I'm going to set x1 depending on beta 1. So if beta is normally distributed with a mean of 0 and standard deviation of 1, what would your strategy be in setting x1? You go with the same sign because you want to maximize, right? So you just pick the same sign. If this is Gaussian, then what is the distribution of y with that strategy? It is essentially a half normal distribution, right? It's a special case, I mean, of half of the folded normal essentially, right? So we can easily get the distribution for something as simple as trivial as, you know, n is equal to 1, right? So now we know what to do, what the benefit is, right? You can take the mean of the half normal. The mean of the half normal is what benefit I will get even before I conduct a single experiment. I can say this much of improvement I can on average expect. The distribution of improvement is a half normal. Now, what happens when it becomes 2? When n is equal to 2, the problem gets a little murkier, right? So it gets murkier because not only is it the sum of two half normals, but now you have this term, and in this term you're not guaranteed to exploit it because if you fixed x1 and x2, x1 and x2 is fixed for you. I can't now go and fix something here to exploit the benefit of beta 1, 2. Beta 1, 2 can go in my favor or can go against my favor. So should I just say the distribution is something like the sum of two half normals plus beta 1, 2 goes for or against you, which won't change the expected value, but it will change the distribution. It will add to the variance of the distribution, right? Is that the right way to think about this? Because I can get the benefits of the first Gaussian through a half normal, the second Gaussian through a half normal, and this guy goes for or against me. If beta 1, 2 is also a Gaussian, it's just a Gaussian that goes for or against me. So I just offset it. Would that be the right way to think? It is not. Anybody have an idea of why that's not the right way to think about it? Again, I'll just give you the simpler version of the problem. When the problem was as simple as this is a Gaussian, you would always set it to, when this is a Gaussian, you would always set x1 to the same sign as beta 1. When you set x1 to the same sign of beta 1, you're guaranteed of a positive y value. So if this is the distribution of beta, the distribution of y, the distribution of max of y, is always a half normal. In this case, now you've got three terms, the first term, the second term, and the interaction term. Can I just think of it as a sum of two half normals plus a Gaussian that goes for or against you? The max of this is not the case where you always exploit first and second. What if beta 1, 2 is significantly larger in magnitude? Would you have actually tapped into the max? Imagine beta 1 is equal to 2, beta 2 is equal to 3. and beta 1 2 is minus 50. Setting x1 and x2 to plus 1 is not the max. Our interest is to find out what is the distribution of the max of y of x1 comma x2, and clearly you have not done that. If you employed a strategy of getting the benefits of this half normal, and that goes for or against you, right? So what is the strategy then you should be following? Maximum magnitude. So rank order the 3 betas, and then you'll always take the first 2. So the second you start thinking of it as top 2, you're already getting into the territory of order statistics, right? Where you're saying the top k. And so that's essentially the strategy that you'll follow. And if you were to follow that strategy, we come up with 2 different ways in which you can quantify the density function of the max of y of x1 comma x2, following a strategy where you always choose to exploit the top 2, and the third one goes for or against you, right? And so we take an order statistics based approach, which is what the PhD student kind of worked on. This is the density function of the top 3 order statistics by themselves. So A is the first order statistic. Just for people who don't know order statistics, it just means what is the distribution. Suppose you take a sample, let us say a sample of k from a fixed distribution. What is the density function of the third highest, for instance, is the branch of order statistics. Third highest. What is the density function of the highest? What is the density function of the lowest? Right? That should also be a random variable, no? Because you're taking a sample from some distribution. So an order statistics based approach where you have the joint density function of a comma b comma c, because there are 3 terms, beta 1, beta 2 and beta 1 2, and beta 1 2 can follow a different distribution from beta 1 and beta 2. And this density function turns out to be the permanent of a matrix, a specific matrix that involves a, b and c. And there is a case where it goes for you and against you, and you can build a density function that way. We also worked on a geometric framework where here a, b and ab are actually the density functions of beta 1, beta 2 and beta 1 2, the specific density functions. And you can also derive in this is as close form as it gets. There's no solution to this, but you can numerically integrate it to, so it's an analytical solution, it's not a simulation of sorts. And we show that both of these should essentially be, we show that they're both the same. So at least so far what we started with is, we started with the problem statement, and then we've said yes, you can trivially solve it for 2 to the power 1. For a 2 to the power 2 matrix also you can solve the problem. That is, before even you do a single experiment, I can tell you the distribution of how much benefit you can get from the process of experimentation if I make assumptions about the density functions of beta 1, beta 2 and beta 1 2. And it should seem reasonable to you that these distributions typically will have, it is not required that they have a mean of 0 or that they are Gaussian, but a mean of 0 kind of makes sense. Like you would experiment on something if you don't know whether it's going to help you or not, like treatment versus control, right? Such. Now, so here are some results that we show from that numerical integration, saying that if this is your distribution of the main effects, this is the distribution of interactions. Again, you see it's not a half normal anymore. It's a slightly more complex distribution. I mean, it's precisely this distribution. This is the CDF of the distribution. Okay, and we give you some indicative results for practitioners. Now the problem gets substantially more murkier when k becomes greater than or equal to 3. And this is where I feel like we've not solved the problem, we've come close, right? We've come up with some solutions for k greater than or equal to 3. When k is greater than or equal to 3, it is not clear which effects can and cannot be exploited. Like, at least with 2 we said, always we can guarantee that the top 2 will be able to exploit. If I tell you there's a, b and ab, I'll rank order them, exploit the top 2. When it's 3, now you have 3 two-way interactions, 1 3-way interactions and 3 main effects. Out of these 7 terms, can I guarantee that you'll be able to exploit the top sum, right? Or how many of them can I guarantee that you will be able to exploit? That is itself really murky, right? And I give you an example of something that can be for or against you, right? Like, so take the case out here where this is the order in which the terms are ranked in terms of their magnitudes. Clearly here you can exploit A, you can exploit AC, and you can exploit B, right? You can exploit the top 3. You can't exploit the remaining 4. It turns out that you can always only guarantee the exploitation of 3 if there are 3 factors. So if there are 3 factors, you have 7 effects, but you can always guarantee the exploitation of only 3. But in this case, you are able to exploit the top 3. Now let's look at the worst case ordering. Here, you can exploit A, you can exploit AB, but you're not exploiting B, which is the third highest thing that you would like to exploit. You have to skip this guy and go and exploit C. Right? So already here, you have an ordering of magnitudes of the betas that is going for you, whereas this is a more pathological case, right? This is like a worst case ordering. It's true that in both cases you can only guarantee that you'll exploit 3. It turns out that for any k, you can only guarantee, for any k, you're always going to have how many terms? K plus kc1, plus kc2 plus kc3 terms. That's always a guarantee. That number is growing big. But the guarantee of the number of effects within that set that you can exploit is always k. That is fairly easy to see. Now, not only is the problem annoying because of the best case and worst case, the problem is further annoying because it is not clear whether it's in your best interest to exploit the top. You could find cases where not exploiting AB has benefits for you in B, but you would have preferred it because AB helped you with, AB is bigger than B, but AB might have a downstream effect on BC, ABC. Collectively, they can form a gang which says that, hey, if you'd mistaken, if you had not exploited B back then, even though he was such a big guy, we could have exploited so many more terms which you are now saying can go for or against you. They would have gone for you, right? And that beauty is something that you're kind of, so I don't know if there is a clean way to say I can exploit these terms. If there is, then we can again derive a distribution for the solution. So now what do? We say let us still go ahead and exploit, assume a heuristic that exploits the top k exploitable terms. Okay, so it's not guaranteed, but the heuristic just says I'm going to go and whichever is the topmost term, and if I can exploit it, I'll exploit it. So in this case, clearly I can't exploit this. So it will have to skip. So is there a pattern to the best case and the worst case orderings? That's what we explore. So what we have done is build a lower bound and an upper bound on the heuristic that says I will try to exploit based on the the terms ordered by magnitude, right? And since this heuristic, since it's a heuristic, the lower bound is guaranteed to be a lower bound on reality. But since it's a greedy heuristic, the upper bound is not an upper bound actually, it's just an upper bound on the heuristic. On reality, it just serves as an approximation in some sense. And so what we are able to show is a pattern that has emerged, and you can kind of reason through the pattern, which is as we saw in the case where there was only one effect, you exploit the top effect, right? Now when there are 2 factors, we are able to say that you want to exploit the top 2 order stats, right? The third order stat and the second order stat. This is the worst case scenario. When there are 3 factors, there are 7 effects, you're able to say I'll always exploit 7 and 6, I might have to skip 5 and go to 4. And then I'm not guaranteed to exploit anything else. So similarly, you're able to kind of write this out for different number of effects, and there is a very clear pattern that starts kind of emerging. The pattern that we are guaranteed to exploit if there are X effects, so in this case there are 63 effects, right? That you can exploit X minus 1, and then X minus 2 plus 2C2, comma X minus 3 plus 3C2 plus 3C3, and so on. So there becomes a very clear emerging pattern on which effects you can exploit in the worst case. Now the best case is fairly trivial, right? In the best case, you can always exploit the top k terms, right? Because there exists some pattern. The simplest way to say that that is the best case is what if the top k terms were the k main effects? They're not related, they don't touch each other, right? So you can always guarantee that you can exploit those. Now, once we're able to identify the pattern for the best case and the worst case, now you use some basic, distributional knowledge on order stats, right? So all of this, if you think of this as these are order stats, right? This is out of the 63 terms, the largest term. This is the 63rd order stat. That is the first order stat. The smallest term is the first order statistic. The cumulative distribution function from an order statistics perspective is fairly straightforward. If all the terms, imagine the 63 terms, right? If they were all coming from the same distribution, it just takes on a simple binomial form, right? You're able to say that this is the rth order statistics. So imagine if this is the 4th order statistic, right, out of 10 terms. Let us say there were 10 terms, and you're asking what is the distribution, the CDF of the 4th term. All 10 terms were sampled from the same distribution. The distribution is called capital F. The CDF of the distribution is capital F. You're asking what is the CDF of the 4th order stat, where you sample 10 order stats, k is equal to 10, right, from a distribution where the CDF is capital F. And that's fairly straightforward, which is you go I is equal to 4 to 10. So these many terms need to be higher and these many terms need to be lower, right? Only then you'll be able to call it the CDF is guaranteed. What we do is expand on this. This is well known. What we do is expand on this for distributions where the main effects and the interaction effects are different. And once we do this, in conjunction with the worst case bounds, and worst case and best case, we are able to come up with actual results on the best case and worst case. And what you can see here, for instance, is the expected value which is determined through simulation versus the lower bound. You can always see that the lower bound is going to work because it's a lower bound on the heuristic. The upper bound is not an upper bound. The upper bound is unfortunately an upper bound on the heuristic, so when you compare it to simulation, it at best serves as an approximation of what reality is without having to clearly simulate. So our main contribution was that we present analytical ways of knowing the possible benefit of running a 2 power k experiment through the use of order statistics. We present upper and lower bounds on a greedy heuristic. And since the bound is on a heuristic, the lower bound is inviolable, but the upper bound serves as an approximation of the expected value. I think that's what I wanted to talk about.